Okay. So far, we haven't really touched programming the GPU. As I've mentioned something, but all we are doing is saying this region of code is going to go into a GPU, but we have not exposed the parallelism of the GPU. So what is really GPU? What are really GPUs for? The first thing is GPGPUs is general purpose graphic processing unit. It just means that there used to be graphic processing units, and now we have them as general purpose computational units. So they are GPGPUs. So CPUs are known to be these really heavy cores, really robust, that have a lot of optimizations that aim to reduce the latency of execution of instructions. So they use high frequencies, like, for example, you can get CPUs running at 4 gigahertz easily, right? Like with turbo boost and all that. They have a lot of out-of-order execution and register renaming and instruction level parallelism techniques for increasing the complexity of the latency of the execution of the program. And they are focused on trying to make a single program run as fast as possible. But in the case of GPUs, it is as if we had a bunch of little workers that by itself, each of them is actually really slow and really not that powerful. That means that they reduce the power consumption of a single worker, and they increase the number of workers. So you may end up seeing power consumptions in GPUs that are relatively high, but they have a really low power consumption per core because the cores are simpler in their way that they are implemented. Right? So they are optimized for throughput. They are optimized such that all of the workers are doing the same thing, the same set of instructions, but working on different parts of data. And so that is the analogy with the ants, the leaf cutter ants, because they are always working on like cutting the leaves of a single leaf, cutting pieces of a single leaf, and they are doing the same operation, but they are a lot of them, so they can end up leaves in like minutes just because they have the ability of being too many. Okay. So that is what the GPUs are good for. They have this idea of doing a lot of things, of having a lot of workers, all of them doing the same thing over and over, but working on different data, okay? So GPUs are usually organized in a hierarchical manner as well. In NVIDIA GPUs, the first group is called the streaming multiprocessor. So when you look at the GPU inside, you will see that it is divided into groups of cores. And each of those groups, of course, is called a streaming multiprocessor. Each streaming multiprocessor has a bunch of cores, what they call the CUDA cores. And when you buy a GPU, they say you have 4,000 CUDA cores or a number like that, that represents how many cores in total your system has. The streaming multiprocessor is going to be accompanied by a register file, and is going to be accompanied by an L1 cache or shared memory, that all of those cores are going to be able to communicate through that shared memory. Cores in a different streaming multiprocessor are not allowed to access the shared memory of a different streaming multiprocessor. And we just repeat this structure on the different streaming multiprocessors. So there is this hierarchical organization of the GPU. More often than not, you also have an L2 cache. And of course, you have the GPGPU memory, which is the abstraction that we had in the past. There is often a host interface that is a piece of hardware that coordinates all the, here is the program that you are going to run, here is the data I want to move, and so on and so forth. And the host and the memory and the CPU are connected through some sort of interconnect. More often than not, that is PCIe, but it can also be NVLink, or it can also be proprietary connections of really specific architectures that you get, especially in supercomputers. Okay, so this is going to be commonly the case. This architecture differs from NVIDIA, AMD, Intel a little bit, but they all have this idea of a hierarchical organization of the cores. They have an idea of a streaming multiprocessor, even though that is called differently in a different architecture. And they have an idea of the shared memory that is often really, really fast for communication between the different cores as well as for the core access. Twice. There you go. So when working with multi-threading, right? So we had these three questions: how to create workers, how to assign work to workers, and how to communicate between workers. We're going to have the same questions for the GPU. How do I create many workers? How do I send work to each of those workers? And how do I communicate between the different workers? So same questions, different architecture, highly parallel architecture. So there is a hierarchical organization in the system. There is the streaming multiprocessor, there are the cores, and in some architectures you get something called SIMD lanes. In NVIDIA GPU architectures, you often do not get that. Okay, so what happens is that because you have these three levels of hardware, you also have 3 levels in the software that specify how you distribute work into the hardware. So the first level is called teams, and when you use the teams directive, you are creating a league of teams, that each of the leagues is just a collection of threads. So the second level is threads, and the threads are often mapped into the cores. The teams are mapped into streaming multiprocessors, and the threads are mapped into the cores. There is the SIMD directive that in NVIDIA's GPUs, it does absolutely nothing in a lot of compilers, but some compilers may use it to optimize the way that they structure assignment of cores, but NVIDIA architectures do not really have SIMD instructions. I'll give an example of what SIMD looks like, but it's not really that important for NVIDIA GPUs. So when you start Pragma OMP target, in reality, you are only using a single core, meaning that you do not have a parallel region, and you are only using a single team, meaning that you are only mapping to a single streaming multiprocessor. And as I said at the beginning, cores in the GPU are actually slower than the cores in the CPU. So if you were to only use the target region, you will lose completely the possibility of having performance in the GPU. The performance in the GPU comes from the fact that you are using all of the cores doing the same operation. And the more similar the operation is, the better the performance tends to be. Then when you create a teams region, what you are saying is you are creating using multiple of these teams, each of them assigned to a different streaming multiprocessor, and each of them having a single thread, right? So there is no parallelism within the streaming multiprocessor, but there is parallelism across the different streaming multiprocessors. A note here is streaming multiprocessors, they do not communicate, and they do not coordinate synchronization operations that well. So it is not the case that you can do, for example, a barrier in between multiple streaming multiprocessors. You have to finish your target region in order to synchronize streaming multiprocessors. You can communicate through memory, and you have atomic operations through memory, but you cannot rely on those atomic operations to be able to do synchronization between the teams, because there is no guarantee whatsoever that if you have many more teams that you have in the system, that you have streaming multiprocessors in the system, there is no guarantee that they are going to be running concurrently. That means that if you are waiting on one streaming multiprocessor for another team, and the other team is never scheduled into a streaming multiprocessor, the core that is waiting for that signal is going to be waiting for it. So you cannot really coordinate, you cannot really synchronize the streaming multiprocessors. They are really decoupled in that manner. They can communicate through memory, of course, and they can access the same memory, but again, they do not guarantee to be scheduled at the same time. So that is quite important. When we go to the parallel, right? So we create a teams, and we are inside the teams region, and we use a parallel directive. What we are saying is we now create the threads within that streaming multiprocessor, and we are going to start taking advantage of the different cores in the GPU. Okay, so we do need teams to be able to take advantage of the streaming multiprocessors, and we need parallel to be able to take advantage of the different cores in the system. And cores within the streaming multiprocessors, they can synchronize between each other. They can have one-to-one communication. They can have barriers. They can have master and single, and they can have all these directives that pretty much what they do is they target synchronization and coordination of working between the different cores. So they are a little bit more tightly coupled than the streaming multiprocessors are. Okay, so it is possible to oversubscribe teams in the system. It is possible to oversubscribe threads in the system. Most of the GPUs are going to let you do that, and they have mechanisms in hardware to be able to do that. And they do have certain limits. Often those limits, especially for threads, are in the orders of more than thousands, 10,000, 100,000 threads. So you can have as many threads as you want pretty much in the system, and you can have also many teams in the system. The teams creates the league, which is just a collection of threads, right? It's a league of threads. Then when you start the team, you have only an initial thread, and the parallel creates multiple worker threads that are associated to the particular teams or bind to the particular teams region. So teams and threads, or parallel and teams, what they do try to answer is how to create workers, right? Not so much how to distribute or assign work to workers, but how to create workers. And again, they cannot synchronize. So in this case, for example, we have pragma OMP target. We are just saying the region of code is going to be executed in the device. But then we say pragma OMP teams, and what we are saying is now we are going to create 10 teams. And then inside of each of the teams, we have pragma OMP parallel. Each of the teams is going to create 10 threads. So in total, I will end up with 100 threads. I know that within the teams, I can guarantee that there is going to be concurrent execution of all my threads, but I cannot guarantee that that across teams, all of the teams are going to be executed concurrently. So if I only have one streaming multiprocessor, the hardware might as well say only one team is executing at a time, and the other teams are just waiting in the back, okay, until the first team finishes the execution. We get the possibility of getting the thread number, we get the possibility of getting the team number, and we can just print the different threads and team numbers, as you will see in the lab later on. Now, parallel and teams only work on creating the parallelism. Work sharing loops is now a way for us to be able to say we have this work and we need to distribute it across the different workers that we have. So OpenMP uses the concept of a canonical nested loop that is just a regular for loop that has to be as simple as you are used to, right? Like you have from 0 to 10, incrementing by 1 or incrementing by 2. You have to guarantee that the order in which those loops are executed are somehow well known. So for example, you cannot have continuous, you cannot have breaks, you cannot have anything that interrupts the regular loop of the iteration space of the for loop. The easier it is for the compiler to understand how you are creating the for regions, the easier it is for the compiler to map those iterations spaces into the different workers. Right, so in this case, we have, for example, for I from 0 to 14, and we are saying I++ at the end. We are just saying the body of the loop is going to be executed 14 times. Each of those iterations are going to have a number that is associated to it, I0, I1, I2, I3, I4, and so on and so forth. So this is what we call the iteration space. It's just all the different iteration values that I have in my iteration space. Now, when I do work sharing loops, what I'm trying to do is I'm trying to assign a chunk of the iteration space to a worker that I have, right? So in this case, I am dividing my iteration space into chunks of 3, and each of the cores is going to be executing those 3 operations. Okay, so core 1, I may have 5 cores here. My iteration space is 15 elements, but the core 1 is going to be in charge of executing 0, 1, and 2. The core 2 is going to be executing 3, 4, and 5. And so on and so forth. So there is this connection in between the workers constructs and the work sharing constructs. So when I have teams, the way that I assign work sharing, that I assign iteration space is through the use of distribute. When I have parallel, the way that I assign iteration space is through the use of for. So I usually say pragma OMP target teams distribute, and I usually say pragma OMP parallel for, which is one of the examples that we had earlier, and we had somebody ask a question about it. I believe it was Isaac, but I may be wrong. And there is also the possibility of SIMD and loop. Loop is a new construct that pretty much tells the compiler, look, I have this loop. I guarantee that the loop is completely independent in the iteration space, so nobody has to go first than anybody else, right? No iteration has to go first. So figure out how you actually distribute it and bind it into the teams and the parallel. So the loop can actually bind to teams, or it can actually bind to parallel depending on the clauses. I'm not going to cover that too much, and I'm not going to cover SIMD other than giving you the idea of what SIMD does. So pragma OMP target teams distribute, what we are doing again, because we are creating only the teams and we are distributing the iteration space in these teams, is we are assigning all the iteration elements of that iteration space into a single core, into a streaming multiprocessor. So we get this, and then we get this, and then we get this. And then when we finish, we may have 5 teams here, but each of those teams can actually go and execute on the same streaming multiprocessor. So these other 3 iterations are going to go here, and these other 3 iterations are going to go here. Or it might as well be the same team. It's just that you are scaling the work of the iteration space differently. Okay, while in the case of Pragma OMP, in the case of Pragma OMP parallel 4, we have the parallelism of the threads, right? So I assume that I am inside of a Teams region and I have a parallel 4 inside. We have the parallelism of the threads and we are assigning each of those threads into those regions, so on and so forth, right? So I am only like chunking the iteration space and putting it into the region. Okay, SIMD. There are certain instructions in certain systems that a single instruction will operate in a register that is larger than the regular size of a register. So in a register in an x86 machine, you get registers of 64 bits and you do addition on 64 bits. But in a SIMD extension of x86, you can get registers of 112 bits. So they are this gigantic piece of memory and they are divided into either 4 or 8 elements, depending on the size of each of the elements. And then the SIMD instruction is going to be in a single instruction executing an operation on all the elements of that register, what is called a vector register. So in a SIMD operation, you have a single instruction that operates on multiple elements through the use of register values that operates on a single, like you do that operation in a single line. In contrary to parallelism through threads, where each of these elements is going to be assigned to a different thread, but each thread doesn't have to be executing the same instruction at the same time. Okay, so SIMD instructions are not common in NVIDIA GPUs because NVIDIA GPU cores do not use SIMD extensions, but they are available in AMD and Intel GPUs. And the SIMD constructs can be mapped to a group of threads depending on the compiler, or they can be ignored by the compiler. So for example, LLVM right now ignores it, but there are efforts right now trying to map the SIMD construct into something that is called the warp in the GPU. Okay, so this hierarchical organization looks like this. We start the OMP target region. We are offloading into a GPU. We create the OMP teams. We are creating a league of teams. Then we go into a distribute. We have the iteration space of the for loop, and we are distributing it across the across the different teams. Then we go into a parallel for, because it's a parallel for. We are also creating a parallel region and distributing this J iteration space in between the different ones. And we get into SIMD, which is also distributing a work sharing loop distribution construct that will take a K iteration space and distribute it across the different SIMD links. So you end up always having this hierarchical organization that looks really similar to a hierarchical organization of the architecture that I showed earlier. So this is a thread team, and this is a SIMD layer. Okay. So some teams restrictions: teams cannot synchronize. I already mentioned that before. Teams do not need to be scaled at the same time, so do not rely on teams to synchronize even through memory because they may lead to deadlocks. Teams must be strictly nested within target regions, so you cannot have Pragma OMP target, then some code, and then create the teams, and then create the parallels. They have to be Pragma OMP target teams right away, and if you want distribute and the rest of the things. So there cannot be anything in between the target region and the teams region, or in between the end of the teams region and the end of the target region. And just putting it all together, we have here a Pragma OMP target teams distribute parallel for, right? Which creates 3 non-teams, which creates 3 teams, creates 100 threads, and it tries to schedule the different work into different threads. You're gonna see a little bit more explanation on the scaling in a second, also in the lab. But the idea here is that we are chunking the whole iteration space of 15, right, into 3 teams, and each of the teams is getting 3 iterations, I0, I1, I2, for example, and then we are assigning those 3 iterations into threads. So here you will end up seeing team 0, thread 0, team 0, thread 1, team 0, thread 2, and then team 1, thread 0, team 1, thread 1, and team 1, thread 2, and so on. You will get an example of this in the lab 4.2.